This is a tutorial to understand discrete probability distributions using the class problem 3.2 Caffe Java. So in this example, we're looking at customer demands for coffee. And specifically, we want to understand the random variable x, where x is the size of coffee demanded. And specifically, x can take on values of none, small, medium, and large. Now we have a number of observations that we've recorded. Specifically, we've looked at the last 10 customers in Caffe Java, and we saw that they ordered the following: none, medium, small, medium, medium, large, none, medium, small, and large. Now, if we count up the frequencies of each of these that have been found, we can look at all of the 4 different values of x. So those are none, small, medium, and large. And it looks like we have 1, 2 instances of none. These are observations. We have 1, 2 observations of small, 1, 2, 3, 4 instances of medium, and 1, 2 instances of large. Now, if we wanted to use this data to predict or to describe a probability mass function, we can use these observed frequencies to infer what the associated probabilities are. Now remember that a PMF is the probability that a random variable, in this case it's x, takes on a particular value we'll call little x. These are examples of little x. So for example, the probability of a customer ordering none is, based on our observations, appears to be 2 instances out of our 10 total observations that we've created. So 2, 4, 6, 8, 10 observations. So 2/10 in this case is a probability mass of 0.2. Similarly, for small orders, we have 2 observations out of 10 total, giving it a probability of 0.2. Medium is 4 out of 10, so that's probability of 0.4. And a large is 2 out of 10, which is probability of 0.2. Now, if you wanted to write this as a formula or an equation, you could say the probability or the probability mass function of a random variable x is 2 if x is none, 0.2 if x is small, 0.4 if x is medium, and 0.2 if x is large. Now, the next step of the problem may want to identify what is the CDF, the cumulative distribution function for this data. So remember from lecture that the CDF is simply the probability that a random variable, in this case x, is less than or equal some value x, some particular instance little x. So in this case, if we think about, there's 20% chance that they order a none. So the probability that they order something less than or equal to none is simply that value, 0.2. Now, what's the probability that they order something less than or equal to small coffee? Well, in this case, there's a 20% chance of ordering none and a 20% chance of ordering a small, meaning that the cumulative distribution function is 0.2 plus 0.2 or 0.4. Similarly, what's the probability of ordering something smaller than or equal to a medium? Well, it's the probability of ordering none, 0.2, plus the probability of ordering a small, plus the probability of ordering a medium. So in total, it's 0.2 plus 0.2 plus 0.4, or 0.8, 80%. And finally, what's the probability of ordering something smaller than or equal to a large? Well, large is the biggest possible coffee size, so we know that there's a 100% chance that they'll order something smaller than or equal to a large. If we wanted to plot these data, so for example, plotting the probability mass function, we would identify the random variable values x, none, small, medium, and large, and we'd draw a bar graph showing the level of these probabilities. So 20% for none, 20% for small, 40% for medium, and 20% for large. Now the corresponding cumulative distribution function takes on these values. So we have none, small, medium, and large. And we know that there's a 0% chance of getting anything smaller than none up until we get none. And then this goes up to a 20% chance of none, of something smaller than or equal to none. And then by the time we go up to a small, the CDF value jumps to 0.4. Right? And then the CDF value for medium is 0.8. And CDF value for large is 1. So the CDF for a discrete variable, discrete random variable, looks like the step function. And it always has 0 on the left extreme and a 100% chance of being smaller than or equal to the largest extreme.